Hello friends, welcome to Event Academy. In the last lecture, we have completed the discussion on the stable and unstable equilibrium. So in this particular lecture, we will discuss about the equilibrium of forces in 3 dimensions. So let's start our discussion. So what we have studied in the equilibrium of forces in 2 dimension. So the condition for the equilibrium of forces in 2 dimension is the resolved part of forces along the x direction is equal to 0 and resolved part of forces along the y direction is equal to 0 and the net moment is equal to 0. Okay, so these are the conditions that are required for equilibrium of forces in 2 dimension. Okay, so in the 2 dimension the forces are coplanar in nature. Forces are coplanar in nature. Okay, so let us start discussing the concepts of equilibrium of forces in 3 dimension. Okay, so first we have to discuss about the resultant of any given number of force acting on a particle. So let us consider a particle at point O and it is being acted by n number of forces. Okay, so let us consider the forces as F1, F2, Fn. Okay, so these are acting at point O. Okay, this is F2, this is F3. Let us consider this as Fn. Okay, so we have the resultant R will be equal to, as per the parallelogram law of forces, R is equal to F1 plus F2 plus this is Fn. Okay, now let us resolve the resultant R along the x, y and z direction. So let us consider the coordinate axis as this is Ox, this is Oy, this is Oz. Okay, along Ox we have the unit vector as I cap. Along y axis it is j cap and along z it is k cap. Okay, so we have the resolved component of R along x direction is R dot I. Resolved component of R along y direction is R dot j. Okay, and we have the resolved component of R along z direction is R dot k. So we have R dot I is equal to F1, resolved component of all the forces, F1, F2 and Fn up to Fn along the x direction is F1 dot I plus resolved component of F2 along the x direction F2 dot I. Similarly, resolved component of F3 along x direction is F3 dot I. Okay, similarly for Fn dot I. So this is equal to, let us consider this whole, the resolved component of all the forces along x direction is x. Okay, similarly R dot j is equal to F1 dot j cap, resolved component of F1 along y direction plus resolved component of F2 along y direction F2 dot j cap. Okay, similarly F3 dot j cap, similarly Fn dot j cap, this is equal to y. Similarly R dot k cap, resolved component of resultant along the z direction, this is equal to F1 dot k cap plus F2 dot k cap plus F3 dot k cap plus this is Fn dot k cap, this is equal to z. Okay, so we have R is equal to x I cap plus y j cap plus z k cap. Okay, and the magnitude of resultant will be, this is equal to x square plus y square plus z square under root. Okay, and unit vector along the resultant, let us consider the resultant like this. This is the direction of the resultant. Okay, so the unit vector along the resultant will be r cap. So r cap is equal to r vector along magnitude of that vector, this is r mod, this is equal to x I cap plus y j cap plus z k cap upon this is x square plus y square plus z square. Okay, so let us write down the unit vector once again. Okay, so we will have the unit vector as, so r vector is, unit vector is equal to r vector upon magnitude of r, this is equal to r we can write as x I cap plus y j cap plus z k cap upon r mod, this is equal to x upon r mod I cap plus y upon r mod j cap plus z upon r mod k cap, this is equal to r cap. Okay, this is the unit vector along the resultant. Okay, what will be the direction cosines? Okay, Direction cosines along the line of action of resultant force. Okay, so let us find the direction cosines of the line of action of resultant force. Okay, so the direction cosines will be x upon r, y upon r, and z upon r. Okay, that is this. These are the magnitude. Okay, so these are the direction cosines. Okay, now let us proceed further. Next concept. So we have one theorem here. The necessary and sufficient condition for the equilibrium of particle under the action of system of forces are that the algebraic sum of resolved part of the forces along the any three mutual perpendicular direction vanish separately. Okay, so let us consider a particle at point O. Okay, and it is acted upon by a system of forces, that is F1, F2, F3, similarly Fn. Okay, so the resultant R will be given by R is equal to x I cap plus y j cap plus z k cap. Okay, where this we have already discussed in the previous slide. So we have where x, y and z are the sums of resolved parts of given forces along three mutually perpendicular axes, that is OX, OY, OZ. Okay, and I, J and K are unit vectors along these axes. Okay, so unit vector along OX, this is OX, this is OY, and this is OZ. So the unit vector is I, J and K. Okay, so we have, let us prove this. So in the first case, let us take two cases. So in the first case, we have to show that case 1, the conditions are necessary. And in second case, we have to show the conditions are sufficient, necessary and sufficient conditions. So in the first case we will show the conditions are necessary, and in the second case we will show the conditions are sufficient. Okay, so the necessary and sufficient conditions for equilibrium of a particle under the action of system of forces are that the algebraic sum of resolved part of the forces along any three mutually perpendicular directions vanish separately. Okay, so we have to show that. So in the first case we have to show that the conditions are necessary. Okay, so the conditions for equilibrium is, so if the particle at O is in equilibrium, then the resultant force will be 0. Resultant force is equal to 0. And what is R? R is equal to x I cap plus y j cap plus z k cap. Okay, so this is 0. This means x, y and z are separately 0. This means x is equal to 0, y is equal to 0 and z is equal to 0. So we have x is equal to 0, y is equal to 0 and z is equal to 0. Okay, thus if the particle is in equilibrium, then the sums of resolved part of these forces along OX, OY and OZ vanish separately. Okay, so these are the resolved part of the forces along x direction, resolved part of forces along y direction, resolved part of forces along the z direction. Okay, so these are getting vanished separately. Okay, so this is given in the question. Under the algebraic sum of the resolved part of the forces along any three mutually perpendicular directions vanish separately. Other way around, we have to show that the conditions are sufficient. So let us work out this. So we have in the case 2, we have the conditions are sufficient. Okay, so we will go other way around. What we will do, if the sum of resolved part of the forces along three mutually perpendicular directions, okay, is 0. So the sum of resolved part of the forces along OX is capital X, along OY is capital Y, along OZ is capital Z. Okay. So the algebraic sum of the resolved part of the forces along 3 mutual directions, if it is 0. Okay, so we have considered this as 0. So this means R, what we have seen, R is equal to X I cap plus Y J cap plus Z K cap. So if this X is equal to 0, Y is equal to 0 and Z is equal to 0, this we have considered. This is 0, this is 0, this is 0. This means R is equal to 0. Okay. So hence, let us repeat this. If the sum of resolved part of the forces along 3 mutually perpendicular axes, that is OX, OY and OZ, vanish separately. Okay, this means X is equal to 0, Y is equal to 0 and Z is equal to 0. This means the resultant is 0. Okay. Okay, so this is the introduction about the equilibrium of forces in 3 dimension. Okay, so we will discuss further in next particular lecture. Thank you.